Okay, so where will be source charge Q, test charge Q naught, and the force between them will be Ke is the electrostatic constant, Q naught by square of the distance R square. Writing it in magnitudically. Now, if this is the force, from definition, the electric field can be written as the force per unit charge. So, F by Q naught, this is actually defined as electric field, and electric field is represented by E. E is electric field intensity. Why do we divide the test charge? Why do we divide the force by the test charge, not by the source charge? Because when we say the force per unit charge placed inside a electric field, that means the force is exerting on the test charge. The source charge is actually exerting force to the test charge. Now, this means if we take a certain amount of test charge and find a particular amount of force in a particular region or particular position of the field, and then taking another test charge having different value and putting on the same place of the field, we will find different force. We don't require that. We require an uniformity, so that using a same test charge we can be able to find all the strengths, all the strengths inside the electric field. Hence, we have to take an uniform amount of test charge, and that will be a unit positive charge. So, unit positive charge is actually the test charge. Now, from the definition, electric field is given by total force by, or electrostatic force by, the test charge, which actually gives the unit force on a unit positive charge. Now, placing this value of F in this equation, we will have this. So, electric field, magnitudically, we can see electric field is Coulomb constant, Q means source charge, and 1 by R square. These are the factors on which electric field depends on. In this expression, you can see Coulomb's constant is a constant, source charge, we have to keep the source charge constant or unchanged in order to have that particular field. So, the only variable is R. That means electric field must vary or is varying with R only. That means the position vector. So, electric field doesn't belong to source charge because it is independent of source charge. We cannot change the source charge for a particular field. It is independent of Q naught, that means it is independent of test charge too. It does not depend on the test charge. We have actually cancelled or defined the dependence of the test charge by putting it unity. So, it only depends on the position vector. That means in this blank we can write the electric field intensity of that point where the test charge was placed. So, electric field belongs to the point within the electric field. Now, we can imagine like that every point inside an electric field have different values of electric field intensity, and when you put certain amount of real test charge on that, we will just multiply that test charge with the electric field, the value of the electric field of that position, and we will get the amount of force that the source charge will exert on that test charge if we place at that position. Hence, electric field is written like that in SI. It can be written as 1 by 4 pi epsilon naught in vacuum Q by R square. Now, electric field is a vector because there is also force. It is nothing but a force. The force experienced by the stationary unit positive charge. Now, electric field is a force. Since it is a force, it is a vector, and obviously the direction, if we give the direction is as same as the force. Now, if the direction of the force can be written by the symbol r cap. R cap is a unit vector in the direction of r. This is r cap. We have chosen the test charge as positive charge. Now, if Q is positive, it will be repulsive. Q is negative, it will be attractive. We have just for general case, we have taken the source as positive also. Hence, we are writing in the positive sense. It is the expression of the electric field intensity. Now we have to write, give the vector notation both the direction, both the side of the equation. So this is electric field intensity, and electric field intensity in SI is 1 by 4 pi epsilon naught Q by R square RT. What is the unit of that? Unit from this equation, you can find the unit. Unit of electric field intensity in SI will be Newton per Coulomb. Just Newton per Coulomb. Dimension can be written from that, very easy. I am skipping that part. So, just we have learnt electric field. What is electric field intensity? Now, we will find the electric field intensity for a point charge. Indeed, it is similar, just similar to the definition. Still, we are using it as an application of finding electric field intensity. So, let us find electric field intensity for a point charge. Let Q be a point charge, source charge. Let Q be a source charge and a test charge. Q naught is placed at a distance r from it. Then force between them will be F is equals to 1 by 4 pi epsilon naught Q naught by R square. Since both are positive, it is R cap. So this is the test charge. This is R and it is R cap. So the electric field intensity is given by E equals to F by Q. This 1 by 4 pi epsilon naught Q by R square. Just like the previous. So it is the unit electric field intensity for a point charge. Now, if we have more than one source charges, let me suppose there is a charge configuration consisting more than one source charge. These dots are all source charges. Say Q1, Q2, Q3, all these charges are source charges. Now they have produced a field. And within that field, we brought a test charge Q0 at a distance r from the configuration or at the very central position of the configuration or center of mass of the configuration. Actually, the distance of test charge cannot be written by a single position vector. We need to find the distance from all the different charges, and let us write it R1, R2, R3, etc. Depending on the nature of these source charges, they will exert force, and we have to find the electric field at that position produced by these source charges. I am erasing this thing because it becomes a bit clumsy and drawing it again. So, what are we trying to do? We have source charges. We have, let us take 3 charges. We have a charge configurations having Q1, Q2 and Q3 as source charge, and they produces a field. So like this is a field, and brought a test charge from outside to that field at certain position. Let the point be A. Let us put the test charge at point A. Now we have to find the electric field intensity at A. This is our problem. How do we solve it? Here comes the superposition principle, what we have used previously in case of Coulomb's law. Here also the superposition principle applies exactly same as that was used or as that was applied in Coulomb's law. How? We can say that if Q1 produces a field E1, Q2 produces a field E2, and Q3 produces a field E3 at that very position A, and so on, then the net field at A will be let us change the it is actually, let us change the heading. It is actually superposition principle. What we are learning is superposition principle. So E total can be written as E1 plus E2 plus E3, and the principle says if we do have more charges, we can just keep on adding those individual fields in order to find the total field at that particular point. And obviously the addition are vector addition. So we just have to vectorically add all the electric fields that the source charges would produce individually on that very point where the other charges were absent. But now the other charges are not absent, they are present, in spite of the fact that they are also influencing themselves, exerting forces. They are also exerting forces to each other. In spite of that fact, we can be able to find the total electric field at that position by adding the individual fields that would have been produced by the test charges individually, independently, when the other charges were not present. What does it mean? It implies that the presence of these charges does not changes the value of the electric field that the first charge would have produced when they are not present. So the electric field of any point within an electric field is independent of the presence or the force exerting on any test charge. That was previously said in Coulomb's law, in case of superposition principle of Coulomb's law, that the force between two charges is actually independent of the presence of the third charge. It will not influence them. So the force are independent and can be added vectorically. So this is the superposition principle which is applied in case of electric field also. And this is just a vector addition. We can write it in the explicit form. Then we have to find the value R1, R2, R3 and write those explicit figures. That E1 is KE Q1 by this is, so we will only take the source charge Q1 by R1 square, R1 cap. Say this is R1. Then it is KE Q2 by R2 square, R2 cap, and so on. So this is the explicit form. Superposition principle. This superposition principle is very important in case of different electrostatic configuration of charges when we have to find the electric field in a given place or required place. So first we have learned what is electric field, that was given in another video, and then we have discussed the nature of the electric field or this Coulomb's law. Then we have defined what do we mean by electric field intensity. Given the form of electric field intensity, find the form of electric field intensity for a point charge. Now we have learned how to use the superposition principle and what are the provisions to use the superposition principle, what are the conditions that has to be followed, and how to find the total electric field in a given position for a configuration of charges. And mind it, we are now doing the charge configuration, which is discrete charge configuration. It's not continuous charge configuration. We will do it in the next class. Today it is discrete charge configuration. Now, after this, we will go to the application part and we will do two applications back to back. First, we have to know what do we mean by dipole, and then we have to find the electric field for a dipole in axial position and in the equatorial position. Dipoles. A dipole. What do we mean by dipole? Dipole are two charges, two equal and opposite charges separated by a small distance is called dipole. When two equal and opposite charges, say minus q and plus q, two equal and opposite charges separated by a small distance, then that configuration is called a dipole. We can see dipole inside molecules where the equal and opposite charges are separated by a very small distance, tiny distance between each other. These are called dipoles, molecular dipoles. We can see dipoles in case of magnet also. North pole and south pole produces a magnetic dipole, but now it is not a magnetic dipole, it is an electric dipole. The electric dipole has two equal and opposite charges separated by a small distance. Let this be the very center of the dipole and the total length of the dipole. There is a trick. We will take it to L, length L, but we will take it to L. Is just for the mathematical ease, where this value is L and this value also L. Just taking it to L for mathematical ease. So dipole is when two equal and opposite charges are placed a small distance apart. And form a permanent charge configuration. Then it is called a dipole. Another thing we have to know is called dipole moment. What do we mean by dipole moment? Dipole moment actually gives how strong the dipole field is. What is strength of the dipole is given by the dipole moment. It quantitatively matches with the product of dipole moment is equal to the product of, it is the product of one of the charges, magnitude of one of the charges of the dipole to the length of the dipole, or and the length of the dipole, and the length of the dipole. So this is called dipole moment. It's a vector. It is denoted by P. P is written as 2ql, where the direction of the dipole moment is from negative to positive. Negative to positive. So this is the direction of dipole moment. Its direction is from negative to positive. So it is dipole moment. We will require these things to find the electric field intensity of dipole. Now let us find the electric field for the dipole, and we have to find it for two positions. First in axial position and next in the equatorial position. So let us find the electric field at axial position and the equatorial position. This position is called axial position. You can see this is the axis. The distance of A from the origin is R. So A is at a distance R from the origin. The origin is set at the very middle point of the dipole. Here is the equal and opposite charges from the same distance away from the same midpoint, that is L, distance apart from O, and L distance apart from positive charge is also L distance apart from O. And the distance of the point where we have to find the electric field is at a distance R from the mid position or the origin O. The total distance of the dipole is taken 2L. Now, according to superposition principle, what we have to do, we have to find the electric field for these two particular charges individually, and then we have to add them up vectorically. So first we have find the electric field for the charge minus q placed at a distance R plus L from the position, and since it is a negative charge, so the direction of the electric field will be, the force is attractive and the direction of the electric field will be in the direction of the negative charge itself. And for the positive charge, the electric field will be repulsive, the force will be repulsive, and it will be in the direction away from the positive charge. And since the positive charge is much closer to the point we have chosen in the axis, so the field strength will be greater. So I have drawn the vector greater, and this vector is smaller, which means the magnitude of this vector is smaller. It is for minus q, it is for plus q. This is just the representation. So let us find the electric field from its definition. It will be K source charge Q, R plus L is the total distance from the negative charge to the point A, and this square, and minus R cap gives the direction of this electric field. Since R cap is drawn in the direction of OA, R cap, and the electric field is exactly opposite to the R cap, so it will be negative of R cap. E positive, that means the electric field for the positive charge, it will be Ke equals to Q by this distance is R minus L. You can see the total distance is R and this amount of distance is L, so the residual distance is R minus L, and the R minus L whole square into R cap. R cap gives the direction of the electric field, and they are same. Now what we have to do, we have to just add them up vectorically. We can also add them up magnitudically or algebraically, because these two vectors are collinear vectors, and we know when we have to add two collinear vectors, in case of collinear vectors, the vector sum are exactly equal to that of the algebraic sum. Since the two vectors are opposite to each other, so the subtraction of these two vectors will give the vector addition of these two vectors, and the axial field will be equal to E minus Q plus E plus Q. We have just taken common Ke and Q and R cap taken as common. So E minus Q, actually I have written E minus Q in the right and E plus Q at the left, and the minus sign is for that minus R cap over here. Here is just the algebraic form. The LCM is this, and the numerator gives a formula of A plus B whole square minus A minus B whole square, which gives 4AB, and the denominator is R square minus L square whole square, A plus B into A minus B whole square. It will all know. From this, over here, the actual position of the electric field, we see that we have just rearranged that thing. This 4RL is divided into 2 into 2 LR, and the Q from here is written over here, so that we can have that 2QL form. This 2QL has a significance from the definition of the dipole moment. We see that the 2QL, 2L is the total length of the dipole, and Q is one of the charges of the dipole, so their product will give the dipole moment. P is the dipole moment here. So instead of 2QL we have replaced P, so the axial field will become 2PR by this. So this is the general form of the electric field at the dipole at the axial position. But from the definition of the dipole, we know that the dipole is something which is a very small distance between the two equal and opposite charges. The length of the dipole is very small. In fact, the length of the dipole is so small that it can be negligible. It can taken as negligible with respect to the distance from the position where we have to find the electric field from the center of the dipole. And so the subtraction R square minus L square leads to R square, since L is much less than R. So in the denominator it will become R square into square, so R to the 4, and here is a R, so it will cancel out and it will become 2 P by R cube. Now there is another thing, physics funda, is that the distance, the direction of the dipole moment is from negative to positive, which is exactly the direction of the residual or net electric field at the point A. Since the positive electric field is greater than the negative electric field, so the net electric field will be in the direction of the positive electric field, that means which is exactly the direction of the dipole moment P. So the dipole moment, we can write the dipole moment vector like that, P into R cap. R cap is the unit vector which gives the which is multiplied by the magnitude of the dipole, gives the dipole moment vector. So multiplying these two things, we can write that. We don't have this negative sign. Why have put this negative sign? Sorry, we don't require that negative sign. It is positive. No need for that negative sign. It's just written it by mistake. So the vector P stands for P into R cap. For P into R cap, we have put P vector, and the electric field become Ke 2p by r cube. What is Ke? Ke is 1 by 4 pi epsilon naught. 2p by r cube is the value of the electric field at the axial position. Now there is a thing it's very important to notice is that we know that electric field always falls for a isolated single charge. Electric field always falls by 1 by r square in 1 by r square or inverse square form. But in case of dipole, the electric field falls by 1 by r cube, which means the rate of fall of electric field is much higher than that of the single positive charge or single charge. That means an electric field of a dipole reduces rapidly with the distance from its center. So this is all about the electric field for the axial position. Now we will start the electric field for the equatorial position. Look, it's a dipole. Its total length is 2L. And the point A is actually placed on the equatorial plane of this dipole, and we need to find the electric field at A. So the formula is same. We have to apply the superposition principle. How? We need to find the electric field at A due to minus q and plus q separately, and then add them vectorically. In order to do that, we have to find the actual distance of the electric field, actual distance of the charge minus q to the test charge placed at A. Also, we need to find the distance of the charge plus q from the test charge A. Now, if we look at the configuration, the test charge is obviously positive charge. The positive charge will repel the test charge, and the direction of the electric field will be in the direction of the force. Of course, the force is repulsive, so the direction of the electric field will be in that direction. That is, we are writing it is E positive. And since this is negative, and it will the force will be attractive and the force will act along the line of joining, so it is the electric field produced by minus charge. So these are the two electric fields. So we have to add these two fields. Now it is a vector addition. We can apply any of the way to find the vector addition. There are several ways to find the vector addition. First of all, we can use parallelogram law, we can use triangle law, or we can split them in component and find the result. So I am just splitting it into components. That will be easier to find the electric field. So let us split it into components. One vertical component, one horizontal component, and another vertical component. These are the components of E positive, and components of E negative is one horizontal and one vertical. These are the components of E negative. So we can see the components of E positive and the component of E negative are opposite to each other. We have to find whether they are equal or not. Let these two angle be theta. This length is L and this length is also L. It's an isosceles triangle because the point A is placed on the equatorial position, so it is an isosceles triangle. The distance from minus q and plus q to A is equal. Since the electric field only depends on the distance, so the magnitude of the electric field, that means E positive and E negative, will be same. Let it be E. Say, since distances are equal. Now, if this angle is theta, it is alternative angle theta and it is corresponding angle theta. So, this horizontal component for E negative, which has the magnitude of E, will be E cos theta. And also the horizontal component for the E positive, which has also the magnitude E, will again be E cos theta, cos component. So it is 2E cos theta, and the two vertical component E sin theta and E sin theta are equal and opposite, so they will cancel out each other. Vertical components cancels out each other, and net field at A will be 2E cos theta. So E equatorial is given by 2E cos theta. Now what is E? From definition, E is the electric field between any one of the charge and the test charge, given by Ke Q by. Now what is that distance? We don't know that distance. We only know this distance, and of course this distance should be given. Let us take this distance as R. Let this distance be R. Oh my God. Let this distance be R. And this distance is L. So that distance will be root over R square plus L square. Is that okay? So, since it is the actual distance from the source charge and test charge, and the electric field is proportional to the square of the distance, so it will be R square plus L square. I am not putting the vector sign here and not also giving the direction. Direction we will find it later. We don't know, of course, the direction. The direction is horizontal and opposite to the direction of the dipole moment, because the dipole moment has a direction from negative to positive, and the total field has a direction exactly opposite to the dipole moment. We'll find it later. So let me put this value here, 2 Ke. I'm taking 2 with the charge 2Q R square plus L square. Now the term cos theta. What is cos theta? Cos theta can be drawn from here, base by hypotenuse, so it will be L by root over R square plus L square. So it will become Ke 2QL by R square plus L square whole to the power 3 by 2, after putting value of the cos theta. So this is the magnitude of electric field at the equatorial position. This is the magnitude only. We'll find the direction afterwards. Now applying the special condition, and the condition for the dipole is very obvious, that R is much greater than L, since dipole has a very small length. So putting this limitation, we can have equatorial is equals to Ke 2QL. Now this 2QL is has a significance. It is dipole moment, already learned. previously. So we can write P by r square plus L square whole to the 3 by 2. This P is a small p, it's not a capital P, it's a small p. Dipole moment is denoted by small p. So what we have is P by, now whenever we apply the limit r is much less greater than L, so r square plus L square will be nearly equal to r square. Since r square plus L square is nearly equals to r square whole to the 3 by 2, it will become r cube. Now, if we put the vector sign, what we have to do? If we give the vector sign, since the EQ is exactly oppositely directed to the vector dipole moment, to the vector represented by the dipole moment, so we have to place a negative sign, since the dipole moment and the net electric field at the equatorial position is exactly opposite to each other, and it will become like that. So more explicitly, EQ can be written as minus 1 by 4 pi epsilon naught P by R cube. So the observation is very clear. Here also the dipole moment, here also the electric field varies with 1 by R cube. That means it falls with a greater rapidity than that of a single charge. But there is also another observation, and the observation is here the direction of the electric field is exactly opposite to the direction of the dipole moment. And if we compare the values of the electric field in the axial and the equatorial position, what we have, E axial by E equatorial will get 2. E axial is actually twice that of the E equatorial. So the magnitude of E axial is twice that of the equatorial one, and the direction is opposite to each other. So this is all about the application of superposition principle, and we have applied here this thing on the dipoles for to have the electric field intensity at the axial position and the equatorial position. On the next class we will learn, we'll start from the torque acting on the dipole whenever it's placed in a uniform electric field, and what will happen if we place it in a non-uniform electric field, and so on. So this is the total volume for electric field. To find electric field, and this electric field we have found using superposition principle for the discrete point charges. Afterward we have to find for the continuous charges. Okay, thank you.